In this video, I'm going to be breaking down the algorithm for the pointillism filter that I'll be implementing for my web app. I'll be breaking down all the classes that I need to implement and all the functions and sub-methods that I need for this algorithm. So to give you context on the web app that I'm building out, what I'm making is a website where I can implement different visual computing techniques and then put it on a website for people to use. So as you can see here, the first thing that I've made so far was I upload an image, and then you can extract out the red, green, and blue channel values. So then the next feature for my web app is that I want to implement a pointillism filter for people to utilize. So pointillism is an art form where an artist can apply many dots into a canvas to create an image out of it. As you can see here, you can create different images and textures and colors by applying different intensities and sizes of different dots and different colors to create different images out of it. And then the reason that I wanted to do this was that I wanted to get more into the artistic side of cinematography and visual effects, but I wanted to come at it from an engineering perspective. Growing up, I was a very STEM-focused kid, so I never got to experience the artistic side of myself. So as I was doing research on how to implement a pointillism filter through code, I came across a Stanford research paper that talks about an algorithm and an analysis of how to apply pointillism onto an image. So what I'll be doing for this feature on this web app is that I'll be reading through this paper and then implementing all the concepts in the algorithm that it talks about, and then put it onto my web app for people to use. So after taking an initial read of the pointillism algorithm paper, I found that this image right here summarizes all the steps that we need to do pretty well. So what we want to do is that we want to pass in two things to our pointillism processor. We want to pass in a bunch of configurations, and we want to pass in our input image. So this processor class will be responsible for orchestrating the entire processing pipeline. So I initialize this processor class. I'll also initialize the preprocessor class, the color palette class, the color transformer class, the image generator class, and so on and so forth. The reason that I'm doing this is that, let's say I wanted to add more steps into the pre-processing pipeline, I can add all those steps into a specific class so that I can keep all of my code logical and maintainable. In the future, if I want to add things like unit tests, or let's say hypothetically in the future, I scale this application and I have like a team of 10 working under me. Making each part of the pipeline its own class makes it so then that an individual team can own this part of the processing pipeline. The other approach that you could take would be you create a main method and then you have all the logic in that one main method. That works too, but I wanted to practice more logical and maintainable code with this approach. The first part of this pointillism processing pipeline is pre-processing. So then the first thing you want to do is that we wanted to apply low-pass filtering. This makes it so then that you blur the image a little bit so then that you can reduce a lot of the aliasing that comes from analyzing the image. And then next you want to downsample the image. This will make it so that you can perform less computations on the image so that you can make it go faster. And the reason you want to downsample the image is that later on in that processing pipeline, we'll do something called dot clustering. And then to take a step back real quick, what I have here is an implementation plan document. So here I have an overview of all the different classes and methods that I want to implement. This is like a visualization of what I want to implement. And then this document right here is a more detailed version of what I want to implement with the exact classes and the exact methods that I want to implement alongside the parameters and the return objects as well. And then the reason for this is that it gives me a very strong plan of exactly the steps I need to implement in order to implement that processing algorithm. So as I mentioned earlier in a pointillism processor class, here I have a class called Pointillism Processor, where in the constructor, I want to initialize all of the other subclasses. So stuff like my preprocessor, my color selector, my color transformer, and my image generator as well. And then here I have a apply pointillism method where I'll do all of these steps mentioned here. So then now if I wanted to pre-process the image, I'll utilize my Pointillism Pre Processor class in order to do that. So for the Pointillism Pre Processor, I want to expose a method called preprocessImage, where it takes in an image, and then the first thing that I want to do is to apply a low pass filter. So we'll apply a thing called a Gaussian blur, and we'll pass in the image and the kernel size. So that'll be the first part of the pre-processing pipeline. And then the next step that we want to do is that we want to downsample the image. And then the reason that we're creating different classes for each step of the processing pipeline is that, let's say hypothetically, I wanted to add another step to the pre-processing pipeline. I can just add another private helper method here in this class and then call it during my pre-process image method here. That way, all the code related to pre-processing will live in the pre-processing class so that everything is logical, maintainable, and all in one class and following solid principles. So then the next step in the pointillism processing pipeline is creating our color palette. The first thing we're going to do is that we're going to utilize k-means clustering to find the 8 most primary colors in our image. So then the reason that you want to pick only 8 colors is that when you're doing pointillism with like an actual paintbrush, there's only so many colors that you can mix. So one of the constraints of pointillism is that an artist would have to blend colors together. So they'll only have 8 primary colors in their tool belt. So by utilizing something called k-means clustering, we can extract the 8 most dominant colors in the image and use that as our baseline. And then the next step is to convert those 8 RGB colors into HSV. When I was reading this paper, I couldn't quite get why we needed to do this, but what I got from it was that RGB colors, it is very difficult to work with brightness and saturation because those characteristics, they're all embedded in all 3 of the color channels. But for something like HSV, it is easier to utilize brightness and saturation with that. So the next step in our processing pipeline is to get the 8 main colors and then convert those colors into HSV. And then the next thing you want to do is that we want to brighten up and saturate the colors. When you do k-means clustering to get the 8 most primary colors, it will typically be a lot darker than what they intended. So then if you wanted to create a more brighter and more vivid image, you want to apply this equation here, so then that you can have a brighter image. And then the last part of this color selection step is to add complementary colors. So the reason that you want to add complementary colors to your color palette is so that you can add contrast to your images. There's a thing called color juxtaposition where if you add 2 complementary colors together, it'll look like they'll be blending it into one. So that gives the image a lot more contrast at the end of it. So with the color selection step in our processing pipeline, I have a class called color palette. And I'm going to expose a method called compute pointillism color palette. Well, I'll take in the image and a couple of configurations to generate the 16 colors that we want to use for our pointillism filter. I then have a helper method called compute primary colors that takes in that original image and returns you a list of the 8 primary colors. I then take those colors and then enhance the color palette by applying this equation onto it. So this equation right here. So this will increase the saturation and the brightness of the original colors. And then I have another method called compute complementary colors that I'll take in that enhanced color palette and then give me a list of 8 more complementary colors. And then after all of this, I'll return a list of the 8 primary colors and then a list of the 8 complementary colors at the end of it. So then the next step in the processing pipeline is called our color transformer. And with this, what we want to create is a list of dot clusters. So a dot cluster will refer to a pixel in our original image. So given a pixel, let's say it is a shade of blue. We want to generate that pixel with the shade of blue by applying a bunch of dots to represent that pixel. For every dot cluster or a pixel, we'll select 3 colors that we want to use. We'll select 2 of the colors closest to that pixel color, and then we'll select a 3rd random color as well. And then with those 3 colors, what we want to do is to solve for this Q equation right here. So this Q1, Q2, Q3, this refers to the weight or the percentage of dots for a specific color. It'll return something like, I want to use 30% of color 1, 40% of color 2, and then 20% of color 3, and that specific dot cluster. So this Q array here gives us the weights of it, and then we then want to solve for N. N refers to the amount of actual dots that we want in that pixel cluster. So we take that, let's say 70%, and then we get a value of 70 dots, for example. And then with this dot cluster, whenever we want to draw in that specific pixel in our output image, we'll say, hey, for this specific pixel, we'll put in 70 dots of color 1, we'll put in 30 dots of color 2, and then 20 dots of color 3. But when you zoom out, the dots in that specific pixel will look like one uniform color. And you do that for every pixel in the image. So it'll look like something like this here. Forgive me, that gets very complicated. I don't know how to explain it very well. And in future videos, I'll go into more details on what this actually means. But for the color transformer step in our processing pipeline, I have a class called color transformer. And I'll expose that a method called transform. Well, we'll take in an image and a color palette from the previous step to generate a list of dot clusters. So I also have a class named dot cluster. We'll have a couple of different values such as the position. So the position of the original pixel in the original image, the color of the original pixel color, select the colors. So when I talked about for a specific pixel or a dot cluster, it is composed of 3 specific colors. That'll be these colors right here. And then I also have a thing called weights and a thing called dot counts. So when I talked about here, these Q values, these are the weights of how many percentage of dots do I need for each color. And then the number of dots refer to N. So the specific amount of number of dots per pixel cluster. So when I initialize this dot cluster, I pass on all of these values, and then I compute the color weights, and then I compute the dot counts here. So these 2 methods will refer to these 2 equations right here. So after we generate all the dot clusters, we then want to generate the actual output image of the pointillism image. So this will be comparable to when an artist actually applies all the dots onto a canvas with a paintbrush. We'll be doing this through code. So what we want to do for this step is that we have a class called image generator, and we have exposed a method called generate. So this will take in a list of dot clusters and a couple of configurations, and then it'll iterate through every cluster and the dot cluster, and then we'll draw onto the canvas here. So whenever we draw a cluster or a specific pixel from the original image, we'll take in all the number of dots and all of its weights and its colors, and then we'll apply all those dots onto the canvas to represent that specific pixel. And then in the research paper, it also talks about how you distribute the dots onto the canvas for that specific pixel, and then it also talks about different brushstrokes and sizes and the orientation of where the dot should go. So all that logic will be encapsulated in this image generator class and its draw cluster method. And then here we have a thing called configuration parameters. So if I were to refer to the cluster distance D, somewhere along this processing pipeline, I'll need to pass in that configuration. So the plan was to pass it to our Pointillism configuration here. And then as I initialize all these subclasses and the subprocesses, I'll forward those configurations into these subclasses here. And with that, after you draw in the image, we'll have the resulting output image of the Pointillism filter applied into the original image. So here I visualize all these steps in the classes that I need to take. And then the reason that I created this document in my code editor and in Cursor is that if I wanted to use AI to implement all of this, I could, pass in this research paper here into Cursor, and then I'll have Cursor refer to this implementation plan markdown file. So then that if I ask it, hey, can you create the Pointillism configuration class? Can you create the Pointillism processor class? I can prompt Cursor to do all of that and refer to this implementation file on how to implement all those classes. That way, instead of relying Cursor to just say, hey, can you implement this algorithm for me given this research paper? I'm pointing Cursor and AI in the right direction of how I want to set up all of my classes. So here, I just give it a skeleton of what I want at a high level, and then I'm going to use Cursor to do the low-level implementation details for me. Cursor is really good at doing very small and specific actions and methods. If you tell Cursor to create the entire processing pipeline, it's going to get confused and hallucinate on a bunch of stuff. But if you tell like, hey, can you apply this specific Gaussian blur for me? Can you apply specifically downsampling for me? Can you apply k-means clustering to generate a color palette for me? The more specific the action is and the method is, the more accurate AI will be. So that's why I wanted to take the time to create an implementation plan so that if I wanted to use AI, it'd be a lot easier to prompt AI to do it for me. And I can go incrementally, step by step on exactly the steps I need to do. For me personally, with this project, I'm going to try to not use AI just so that I can learn and understand all the concepts that I need to implement. Things like k-means clustering, filtering, color quantitation, all that stuff is going to be very important for me for future projects and features that I want to implement for this web app. So I'm going to do my best to not use AI as much as I can. But I do want to see how well AI would do if I were to prompt AI to be like, hey, can you just implement this processing pipeline for me? Refer to the implementation plan and refer to the PDF file of the Pointillism paper that I just talked about here. So I hope you guys learned something new of how I break down a research paper into different classes and subclasses and methods that I want to expose in order to implement an algorithm. By doing this, I create classes and methods that are logical and maintainable so then that if I wanted to extend on a bunch of this functionality in the future, I have an easy way and a maintainable way to add all this functionality into the different subclasses that I created for this. And in future videos, I'm going to be implementing all the different steps of this processing pipeline so then that we can add it onto our web app. So with that, hope you learned something new, and I'll see you in the next one.